Today I'm going to present to you several new example-based techniques for graphical editing. When I refer to graphical editors in this talk, I'm going to mean 2D object-based graphical editors similar to MacDraw and Adobe Illustrator. Although the techniques that I talk to you about, many of the techniques can be extended to 3 dimensions and other domains. But the motivation behind this work is to make graphical editing easier. There are 2 different kinds of tasks we want to make easier. We want to make the cognitively difficult tasks easier, such as complex constructions. But we also want to make the repetitious tasks simpler to perform, such as changing all of the graphical attributes of a set of objects. We also want to make graphical editors more extensible. If the editors are more extensible, users can customize the editors for their particular tasks and can become much more efficient. But also, expert users can encapsulate their knowledge into a form that other users can benefit from, such as macros or complex replacement rules. The approach that we take for achieving this extensibility is exploiting example-based techniques or demonstrational techniques. We don't want users to have any particular programming skills in order to take advantage of these techniques. We want these techniques to be accessible to all users of our system. The testbed for this research is Chimera. Chimera is actually an editor framework or an editor substrate. It contains smaller editor components for editing graphics, 2D graphics, interfaces, and text. All of the techniques that I talked to you about here are accessible within the graphics and interface editing modes of Chimera. Chimera is a testbed for 5 different example-based techniques: graphical search and replace, constraint-based search and replace, constraints for multiple snapshots, editable graphical histories, and macros by example. I'll talk to you about each of these techniques in sequence and show you videotapes of them in operation in the Chimera editor system. At the end, I'll discuss each of these techniques and mention how they interrelate, how all of these components form a greater whole than the individual parts. There's a large amount of related work. The first 2 pieces of work here refer to techniques for making it easy to make repetitive changes throughout documents. At MIT, Ivan Sutherland worked on Sketchpad, which was one of the first graphical editor systems, and it introduced the concept of instancing. In instancing, the user can define library objects and instantiate the library objects multiple times throughout a graphical scene. And changes that are made to the library objects automatically propagate to all of the instances. Robert Nix, while he was at Yale, developed a text editing by example system. His system could infer fairly complex textual search and replace operations by demonstration. And then the next two systems refer to algorithms for inferring constraints from a static scene. Chimera, my editor system, also infers constraints. Theo Pavlidis worked on an automatic illustration beautification system. His system would look through a roughly drawn illustration for relationships that were almost fulfilled and establish them precisely. And Brad Myers in his Paradox system developed some algorithms in order to infer constraints among objects forming user interface widgets. And the final 2 pieces of work are both programming by example systems, and Chimera has a programming by example component as well. Dan Halbert worked on the Small Star system while he was at Xerox. Small Star was a mock-up of the Star user interface, and he worked on a programming by example system for programming the Star user interface by demonstration. His system used post-facto generalization, which is a technique that I also take advantage of. I'll talk to you about that later on. And more recently, Dave Malsby worked on MetaMouse, which is a graphical editor that can infer procedures by demonstration. His system concentrated on inferring loops and conditionals by demonstration. My system focuses more on representational issues. The first technique that I'm going to talk to you about is graphical search and replace. Graphical search and replace is basically the analog to textual search and replace in text editors. The motivation here is the desire to make repetitive changes throughout a graphical document? Well, there are other ways that you can make repetitive changes throughout graphical documents. I mentioned instancing in the previous slide with respect to Ivan Sutherland's Sketchpad system. Commercial graphical editors such as MacDraw all have a grouping operation which allows the user to select multiple objects and to place them together in a group, and this group can in turn be selected and the graphical attributes of all the objects in the group can be modified at once. The disadvantage of both of these techniques, however, is that they both require special structuring of the document. If the user during document construction time doesn't know how the document needs to be structured in order to make subsequent coherent changes, repetitive changes easy, then they're out of luck. If they didn't perform the necessary grouping operations or they didn't make the proper instances, then neither of these techniques will help them. In contrast, graphical search and replace requires no special structuring of the document. I'm now going to show you a videotape of graphical search and replace in action in Chimera, and then I'll talk to you more about it.
Graphical editing can be a difficult process and involve many repetitive tasks. To remove some of the tedium and make the job easier, we have developed a number of example-based techniques. These techniques, which I will demonstrate in this videotape, have all been incorporated into the graphics and interface editing modes of Chimera, an editor that we have built to serve as a testbed for research and demonstrational interfaces. At the right of the screen is a Chimera graphical editor window. This window contains a gray equilateral triangle. To the upper left is the Match Tool window. Match Tool is a utility for graphical search and replace. Graphical search and replace is useful for making repetitive changes to graphical properties or object shape. In the upper left-hand corner of the Match Tool is the Search pane, a fully editable graphical canvas in which objects can be drawn or copied. This pane contains the search pattern. Similarly, in the upper right-hand portion of the Match Tool window is the Replacement pane, which contains a replacement pattern. Below these windows are rows of graphical attributes, followed by two columns of checkboxes. The first column of checkboxes specifies which attributes of the object in the search pane will be used for the search. The second column indicates which properties of the objects in the replacement pane will be applied to the match. Here we have specified a pattern to find equilateral triangles of any scale and replace them with three smaller triangles while keeping the match's original graphical properties such as color. We now look at the graphical editor scene again. When I press the Change All button in the Match Tool, the gray triangle is subdivided into three smaller gray triangles. If I now select Fill Color in the Replacement column, when a replacement is performed, the new triangles will get their colors from the triangles in the replacement pane. Once more, I press the Change All button in the Match Tool, and the equilateral triangles are subdivided again, but this time they receive their colors from the replacement pattern. Now I'm going to select Fill Color from the Search column and deselect it from the Replacement column. Since the Search pane contains a yellow triangle, the Match Tool will search only for yellow triangles, and the replacements will be yellow. I press Change All, and the yellow triangles subdivide. I press Change All once again, and the smaller yellow triangles are subdivided. I press Change All a final time, and get even smaller triangles. Graphical search and replace can be used to create shapes such as these, formed by graphical grammars, but it's also useful for more mundane editing tasks.
Okay, I mentioned at the end of the videotape that graphical search and replace can be used for things other than generating shapes from graphical grammars. Here's an example of this. Here we've drawn a picture of a yellow jay in an oak tree. Well, it turns out that yellow jays don't live in oak trees, they live in maple trees. So how can we take this picture and transform it into the picture below? One way that we can do this is through graphical search and replace. Here's a graphical search and replace specification that does the trick. Here we're looking for all objects of this shape with the same set of graphical properties, the fill color, the line width, the line dash, etc. And we're replacing objects that match with objects such as the one in the replacement pattern with the same shape as the object in the replacement panel, plus the same fill color, line width, etc. We're also searching for these objects at any rotation and any scale. So there are a number of additional search and replace parameters aside from rotation and scale invariance, which I just mentioned. There's the shape tolerance search parameter, which allows us to adjust how closely objects in the scene must match the object in the search pattern in order for it to be considered a perfect match. Also, there's the polarity option. When polarity is turned on, two objects must be drawn in the same direction in order for them to match. Granularity allows us to adjust how much scene structure is used when performing a match. We can match for objects anywhere in the scene, only at the object level, and only at the group level, according to the granularity that we specify. Also, we can search for objects in the presence of other objects, essentially perform a context-sensitive search. Now, the match tool can find similar shapes regardless of the representation. To do so, it converts all shapes into an intermediate representation, a polyline form. So the first step in performing curve matches in the match tool is to take all curves in the system and convert them into a polyline representation. This polyline representation is adaptive, so regions of high curvature are represented by more segments than regions of low curvature. The next step is to put the polylines into a canonical form that essentially factors out those transformations that we want to ignore. So the first step of putting the polylines into the canonical form is to find the center of mass of the polyline and also a starting point for the polyline. In the case of open curves, the starting point is the first vertex of the polyline. In the case of closed curves, the starting point is the vertex that's furthest from the center of mass. And in some cases, there can be more than one starting point. Now, since we always want to factor out translations in performing our matches, we always perform the second step. We factor out translations by translating the polyline so that its starting point lies at the origin of our coordinate system. If we're performing rotation invariant matches, that is, if we want to ignore rotations, we then rotate the polyline so that the center of mass lies along the positive x-axis. If we're performing scale invariant matches, if we want to ignore scales, then we scale the polyline so that it has an arc length of 1. The third step is to perform a set of quick reject tests in order to immediately determine whether two polylines definitely do not match. For example, we compare the arc length of the polylines and the maximum distance to the center of mass. If it still appears that the polylines might match, we have to perform a more complex polyline comparison that takes into account possible differences due to rasterization.
Question?
Yeah.
Did you do any experiments on the discrimination power of different tests, or is the maximum distance to center of mass as good as you can get?
You're talking about in the third step.
Quick reject test.
Well, there are actually three different tests that we use. One is maximum distance to center of mass. The other one is arc length, and I forget what the third one is offhand. And these work fairly well. Now, there are undoubtedly other metrics that we could use as well. We could look at various moments of the shapes. There was some research done by Michael Rabin in which he does shape matching by computing a very complex fingerprint for every curve, a fairly complex hash number. And he just compares the hash numbers and figures, there's such a small chance of two hash numbers serendipitously turning out to be the same. But that's a valid way of comparing curves. So graphical search and replace can be used for a number of other applications aside from just making simple repetitive changes to write a graphical document. We've used graphical search as part of a graphical grep mechanism. We created a facility that allows us to search through graphical scene files for a particular set of shapes. One of the components of this research is a macro by example facility that I'll be talking to you about later on. Graphical search can be used as an iteration construct for these macros. We can search the scene for all red triangles or all green squares and perform a particular macro for these objects, on these objects. You saw in the videotape an example of graphical search being used in order to generate graphical grammars. Here's another graphical grammar that you're all probably familiar with. There we started out with an equilateral triangle. We replaced single straight segments with a set of 4 segments and iterated a number of times to produce this snowflake curve. Well, this was a very simple search and replace specification. It was very easy to generate this shape using graphical search and replace. Here's a more conventional means of producing this shape. Here's an advertisement from MathCAD showing you how easy it is to generate snowflake curves. Here's code to do so, and a bit of a challenge later on, if any of you are interested, is trying to figure out exactly what they're doing in this code to generate a snowflake curve. I mentioned another application of graphical search and replace is graphical templates. Since it's much easier to draw simple shapes than it is to draw complex shapes, it's often easier to draw a skeletal version of the scene that we're interested in and use graphical search and replace in order to add the extra scene complexity. So in order to draw the initial picture of the yellow jay in the oak tree that we saw earlier, I drew this picture of a yellow jay in a skeletal version of a tree. And here, this is actually a color picture, and the segments that we want to be replaced by leaves are all black here, and the other segments are different colors. So we perform a search, a rotation and scale invariant search on black lines in the scene, and we replace the black lines with the oak leaves. Yeah?
Do you have a facility for sort of randomness within the replacement pattern so that you can...
No, we don't, but that's something that I've thought about a bit, and I think that would be useful. It would be nice in order to be able to preview the replacement a little bit. I definitely agree with that. Well, I just talked to you about graphical search and replace. Graphical search and replace has a limitation as we currently defined it and implemented it. Even though we can search for complete shapes in the scene, we can't search for particular geometric relationships. So, for example, we could search for equilateral triangles in the scene, but we couldn't search for any triangle containing a 60-degree angle. Furthermore, we can replace complete shape. We could replace any equilateral triangle with another particular kind of triangle, but we couldn't just change one particular angle of a triangle. So we've developed another technique called constraint-based search and replace that gives us better selectivity in both the search and the replacement patterns. It has a number and it does so through the use of constraints. It can be used for a number of different things. It can be used in order to infer a number of constraints in a static diagram. It can be used in order to neaten up roughly drawn illustrations. And it can also be used for fairly complex picture transformations. I'll give you examples of all of these in the talk and in the videotape that I'll show you now.
Graphical search and replace can be used to search for exact shapes in a scene, but it cannot be used to search for particular geometric relationships. We have developed another technique called constraint-based search and replace that performs such tasks. Below the Match Tool window is the Rule Tool. The Rule Tool is a facility that allows users to archive collections of graphically defined search and replace rules. I select a rule that I had defined earlier, called Make Line Tangent to Circle, and press the Put button to copy this rule into the Match Tool window above. This rule finds lines that have endpoints nearly tangent to circles and makes them precisely tangent. To the right of the Match Tool is the Constraint Tool, a utility for viewing and editing constraints. Constraint-based search and replace rules can contain constraints in both their search and replacement patterns. We are now using the Constraint Tool to view the constraints in the search pane of the Match Tool. The search pattern contains 2 constraints. As I select a constraint in the Constraint Tool, a graphical representation of that constraint is drawn in the editor scene. Here is a distance constraint that specifies that the top vertex of the line must lie on the circle. The scene also contains an angle constraint that the angle between the center of the circle, the top vertex of the line, and the bottom vertex must be 90 degrees. Together, these constraints specify that the line must be tangent to the circle at an endpoint. The illustration in the search pane does not satisfy these constraints exactly. It provides the tolerance of the search by example. Objects in the scene that fulfill these constraints at least as well as the search pattern are considered valid matches. The replacement pattern also contains constraints. It contains both constraints of the search pattern, the constraint that one endpoint lie on the circle, and also the 90-degree angle constraint. When a replacement is made, these constraints are applied to the matched objects. However, there are several additional constraints in the replacement pane. There are a number of ways to make a line and circle tangent. We can move and grow the circle. We can translate the entire line. Here we show additional constraints that specify that for our solution, we want only the vertex near the circle to move. We have loaded into the Chimera editor a scene containing lines and circles. The replacement pattern will take lines nearly tangent to circles and make them tangent. I press the Change All button in the Match tool, and the scene is promptly transformed according to the user-defined replacement rule.
So as you saw in the videotape, we have constraints both in the search pattern and the replacement pattern. The constraints in the search pattern specify which relationships we're looking for in the match. Also, the tolerance of the search is provided by example in the search pane. All objects in the scene that match the search pattern constraints at least as well as the search pattern objects are considered valid matches. In the replacement pane, there are actually two different kinds of constraints. The first kind of constraints, called set constraints, specify which new relationships we want to be establishing in the match. However, we also have a second kind of constraint, fixed constraints, which specify which relationships we want to remain invariant when the match is found and the replacement is performed. For example, in the videotape, we had an example of making a line nearly tangent to a circle at an endpoint tangent. Well, we had fixed constraints. We added fixed constraints to the scene in order to say that only the top vertex of the line, the vertex nearest to the circle, would be allowed to move. If we didn't have these constraints, then the replacement rule might take this scene and turn it into this scene, where the circle has grown and shifted slightly. Finally, we have a demonstrational heuristic that we use in order to have the system figure out whether the user intended fixed constraints or set constraints, and it works very well. If any of you are interested in this, we can talk about it later on. Well, constraint-based search and replace needs a number of additional search and replace parameters, aside from the ones we had in traditional graphical search and replace. We've added a new parameter called constraint permanence, which determines whether or not the constraints that we add to the scene in order to perform a replacement are left in the scene after the replacement is performed. For example, if constraint permanence is turned on after we made all the lines in the scene tangent to circles, we could grab the far joint of a line that was tangent to a circle and move it, and it would remain tangent to a circle. In traditional graphical search and replace, in our original graphical search and replace, we would only allow an object to match once during a search. It turns out this is not the desired effect most of the time in constraint-based search and replace. Let me explain why. Let's say we're looking in the scene for all angles that are nearly 90 degrees. Well, we'd want to match on this angle, and we'd also want to match on this angle. So this middle vertical segment should be part of two different matches. So the match exclusion parameter allows us to tell the system whether or not we want to allow these multiple matches. We've developed the rule tool, which is essentially a constraint-based search and replace archiving facility. We can save rule sets in the rule tool. We can also select rules within the rule tool and apply these to the scene as though they were a single rule. We've also built a dynamic search and replace facility. This allows us to apply activated rules in the rule tool to the scene whenever the scene is edited. If dynamic search and replace is turned on, for example, and we add a line to the scene that's nearly tangent to the circle, and we have the rule we defined earlier activated, then both of these objects become highlighted, and the system asks, do you want to apply the rule, make nearly tangent line to circle completely tangent? Here's another application of constraint-based search and replace, scene or illustration beautification. Here we have an instance of the rule tool, and we've defined a number of rules, and we've activated a few of these rules. We've activated the rule to connect nearly connected segments, and make angles that are nearly 90 degrees, and to make segments that are nearly horizontal, etc. And we apply the activated set of rules to the picture on the left, and we produce the picture on the right. So we take this rough version of the house, and we need using constraint-based search and replace. Here's an example of a rule that basically goes beyond mere scene beautification. Here we define a rule that finds all 90-degree angles in the scene and rounds these angles. It does so by splicing in an arc such that tangent continuity is maintained at the arc's endpoints. It's a fairly complex rule, as you can see, and I imagine most of the users of the system would probably not be able to define this rule on their own. However, that's where knowledge encapsulation comes into play. Since expert users can archive rules using the rule tool, that they can create libraries that the entire user community can benefit from. There's a few comments on the complexity in the implementation. Generalized graphical constraint-based search is an NP-complete problem. You can view the task of finding one constraint scene within another constraint scene as the task of finding one graph within another graph. You can view a constraint scene as a graph where all of the objects in the constraint scene are nodes of the graph, and constraints between the objects are edges. So finding one constraint scene within another constraint scene is basically finding one graph within another graph, which is the subgraph isomorphism problem, which unfortunately is NP-complete. Well, there's good news, though. For a fixed size pattern, and all patterns in the system are fixed size, the cost is polynomial. So, and typically, the cost is very low, either linear or quadratic, since the pattern sizes tend to be fairly small. In fact, I've never had the need nor desire to define a pattern that was more complex than order n cubed. All of the patterns that you have seen today are either order n or order n squared. When we're performing the match, we can actually use constraints in order to prune the search space, in order to make the search more efficient. Here's how we do so. Let's say we're looking in the scene for two lines that are connected together. That is, there's a 0-inch distance constraint between both of their endpoints. And we found a tentative match for the first segment in the scene. Well, we know where to look in the scene for the other segment. We know that the other segment must have an endpoint within a disk of one of the endpoints of this first line, where the radius of the disk is determined by the tolerance of the search. When we solve our constraint system, we use Levenberg-Marquardt iteration, which is an optimization technique. It allows us to solve both under-constraint systems and over-constraint systems. It's a very robust constraint solution technique. Well, constraint-based search and replace is essentially a technique for inferring constraints from a static scene according to user-defined rules. Unfortunately, there really isn't enough information in many static scenes to infer all the constraints that we would want. So we've developed another technique called constraints from multiple snapshots that allows us to infer constraints from a dynamic scene. Basically, the user presents the system with a set of valid configurations of a set of objects. And the system automatically determines which constraints from its internal constraint set hold among all of these separate snapshots. And the system can instantiate these constraints. When the user turns constraints on, they can manipulate the objects, and they'll be constrained according to the constraints that were inferred by the system over the set of snapshots. At any point in time, the user can turn off constraints and specify another snapshot if they desire. I'm going to show you a videotape of constraints from multiple snapshots that might give you a better example, a better idea as to how this technique works. And then I'll provide you with a few additional examples and then explain the algorithm.
Constraint-based search and replace is a mechanism for inferring constraints from a static scene according to user-defined graphical rules. Sometimes it's difficult to infer constraints from a static scene, but using another technique, constraints from multiple snapshots, Chimera can infer intended constraints from several configurations of an illustration. In the Chimera editor scene on the right, we have a horizontal line and a quadrilateral. We want the editor to generate constraints such that the two middle vertices of the quadrilateral will remain fixed in space, and we want the quadrilateral to remain a rhombus. We also want the horizontal line to remain to the right of the bottom vertex of the rhombus at the same height and x offset. Initially, we take a snapshot of the scene by pressing the snapshot button in the constraint tool. Next, we edit the scene into another valid configuration. We make the rhombus taller by dragging the bottom vertex and the top vertex, and we move the horizontal line to be level with the bottom vertex. Next, we take another snapshot of the scene. Now let's view the constraints that the editor found. These are listed in the constraint tool. The first constraint is that the left angle must be equal to the right angle. The second constraint is that the top angle must be the same as the bottom. There are other constraints as well. Now let's turn constraints on. I'll select the horizontal line and move it. I'll move it upwards. The rhombus resizes accordingly. I can also select the bottom vertex of the rhombus and move it down. The top vertex and the horizontal line move accordingly. The constraints in our system are multi-directional. I can select the top vertex and drag it, and all of the other objects reconfigure correctly.
Here's another example of constraints for multiple snapshots. Here we apply the technique to the user interface domain. We've drawn a picture of a window in the interface editing mode of Chimera, and we've placed 3 buttons along the bottom such that they're equally spaced. We've placed a scroll bar on the right-hand portion of the scene, and we've placed an application canvas basically from the left edge of the scroll bar to the left edge of the window. So we take a snapshot of this initial picture. Then we move the objects, we shift the objects to provide another example for the system. Here we've made the window a little bit wider and significantly shorter, and we've respaced the buttons, and we've moved the scroll bar and replaced the application canvas, and we've provided another snapshot. Finally, we turn constraints on and grab the upper right vertex of the window and move it, and the buttons automatically space correctly. The scroll bar stays on the right of the window, and the application canvas stays correctly in the middle. Here's a slightly more complex example. Here we teach a Luxa lamp how to move. We've drawn a picture of a Luxa lamp in the graphical editor, and we've created this beam direction dial that we intend to always point in the same direction as the lamp head. So we take an initial snapshot of the scene. We then rotate the various components and take another snapshot. And we, in this particular case, since the scene is fairly complicated, we provide a third snapshot as well. After this, we turn all of the constraints on and manipulate the lamp. We grab the top joint of the lamp, which is really just a circle in our graphical editor, and we move the beam direction dial, and the various arms of the lamp remain connected. They don't stretch, they remain rigid bodies. And the lamp head always points in the same direction as the beam direction dial. Here we grab the top joint again and move it, and move the beam direction dial a second time. And here I think we just changed the beam direction dial. We use a fairly interesting algorithm in order to infer constraints from multiple snapshots efficiently. To do this, we've developed the concept of a transformational group. A transformational group is a set of vertices that have been transformed together since the very first snapshot. If a group, we can very efficiently, very quickly determine all the constraints that hold within a given transformational group. For example, if a set of vertices have only been rotated together since the very first snapshot, we know that though the slope between any pair of vertices in the group will have changed, the distance between the vertices will have remained invariant. Thus, there would be the implied fixed distance constraint between all pairs of vertices in this transformational group. Similarly, the relative slope or angle between sets of 3 vertices in the rotational group will not have changed. And the relative distance, or the distance between 2 pairs of two vertices, the proportional distance between 2 pairs of vertices, will not have changed. If a group had been rotated and scaled, then the relationships that we would immediately know to hold within that rotational scale transformational group would be the logical and of these 2 rows of the table. So the algorithm works as follows. For each snapshot, we split existing transformational groups into new transformational groups if the subset of their vertices has been transformed independently. In the next step, we find intergroup constraints between a newly split off transformational group and its parent transformational group. In the third step, we examine all of the previously instantiated constraints to find out if any of them have been violated. If some have been violated, we don't throw them away, but we save them to be used in step 4. Here's an example of the use of violated constraints in order to create a new kind of constraint, relative constraints. Okay, so let's say after the initial snapshot, we have a fixed distance constraint on the first segment, a fixed length constraint that says that this must be 1 unit long and the second segment must be 2 units long. After the second snapshot, the first segment has become 2 units long and the second segment has become 4 units long. Well, both of the fixed length or fixed distance constraints that we had in the initial snapshot are violated. However, instead of throwing them away, we put them in bins according to how much they've been broken. So both of these broken fixed distance constraints get put in bins that say they've been broken by a factor of 2. In the fourth step, we examine all of the constraints that have been broken together by the same amount, and we create relative constraints among them. So here we could create since both of these fixed distance constraints have been broken by a factor of 2, we create a relative distance constraint that says that the first distance must be proportional to the second distance. In the fifth step, we filter out redundant constraints. Even though our system finds all of the constraints in the constraint set of interest that hold among a set of snapshots, it doesn't find the minimal set. There are redundant constraints in the set, and since constraint solvers work more efficiently when there are fewer constraints, we try to find the redundant constraints, or at least as many as we can find, and remove them from the system. We've also built a new history mechanism for graphical user interfaces as part of Chimera. This history mechanism is called editable graphical histories. Histories are important in graphical user interfaces and, in fact, all user interfaces for a number of reasons. Histories allow the user to scroll through the operations they had performed in a session and review what they had done. Histories are necessary for undo and redo. And histories can also support macro construction in a number of different ways. I'll be talking to you about macro construction later in this talk. In order to support all 3 of these different tasks, it's important that the user be able to understand the history. The user has to be able to understand the history representation that the system presents. Well, there have been a number of different history representations that have been used in the past. The text-based world also often uses the spatial browsing technique. In spatial browsing, commands are listed one after another in a sequence, and the user can scroll through the sequence to see the list of commands that they've performed. An example of this is the C shell. In the C shell, the user can type history and see the list of commands. Well, this works very well for the text-based world, but it doesn't work very well for the graphical user interface world, where the position of objects on the screen and graphical properties can have an important impact on their interpretation, on the operations interpretation. So in the graphical user interface world, many applications use temporal re-execution, where the user can play back the operations that have been performed in the application. Essentially, they can scroll backwards and forwards in time and see in the application canvas the effects of the various operations that they have performed. Well, temporal re-execution has a number of problems, one of which is that it doesn't really provide very much context to the user. At any given point in time, the user can be viewing only one brief moment of the history. It's basically like trying to edit a document in a line editor. trying to view the history through temporal re-execution. So we've developed a new technique which is a hybrid approach that adopts particular aspects of temporal re-execution and spatial browsing. And we call our technique editable graphical histories. Editable graphical histories follows a comic strip metaphor where the system provides a set of panels where the important operations in the history of the user interface are distributed among the set of panels, with at least one event per panel. Editable graphical histories use the same visual language as the interface itself, so all users of the system can understand the history representation. An advantage of editable graphical histories is that they allow the past state to be viewed without the user having to undo or redo the operations that they've performed. I'm now going to show you a videotape of editable graphical histories within Chimera.
We've also developed a new visual representation for commands in a graphical user interface. This representation is called editable graphical histories. At the top right of the screen is a Chimera editor window. To its left is a control panel, and below is a graphical history window. As I draw in the editor window, panels appear in the history window below. The history follows a comic strip metaphor, where important events are distributed over a sequence of panels. We follow several strategies to make the histories more manageable and more readily understood. Sequences of related operations are coalesced into individual panels. For example, the 5 add-line operations that I executed to draw the polyline are coalesced into a single panel. I can use an interactive elaboration mechanism to expand this panel into lower-level panels or to coalesce them again. If we were to represent the entire screen in each panel, it would be difficult to see the panel's action. Instead, we zoom in on the region of the scene where the change was made. We also include a little bit of scene context to show where the operation was performed. We render the panel objects in a graphical style according to their role in the explanation. Contextual objects are subdued by lightening their colors. I'm now going to create a circle in the editor scene. Next, I select and copy the circle a number of times. All copies are coalesced into a single panel. Histories can be used to review operations that have been performed during a session with an application. They can also be used for undo and redo. I can make the panels editable by selecting a checkbox at the bottom of the history window. Now all panels become fully editable graphical canvases. I am now going to select the circle in the history panel right before the copy operations. I'm going to change its color. I'll type a shade of yellow into the text input widget and execute the change color operation. The circle in the panel has become yellow. Now I can select the panel and ask that its changes be propagated into the history. The graphical editor scene updates itself. The original circle and all of its copies are now yellow. The history window is also updated. The command that I executed in the panel is now inserted into the history, and the color of the circle copies in the history are also updated. I can also delete operations from any point in the history. Here I select the panel containing the 5 add-line operations, and then execute the delete selected panels operation from the history menu. The editor scene now appears as though these operations never happened. The selected panel is also deleted from the history window. Graphical histories are useful for reviewing, undoing, and redoing commands. They can also be used as the basis for a macro by example or programming by example facility that we have also incorporated into Chimera.
History creation consists of 4 basic steps. Whenever the user is performing operations in our editor, the system is recording the operations that have been performed. It's also recording a set of operations that allow us to undo the user-executed commands. So the system's saving both undo and redo operations. In the second step, the system partitions the operations that have been saved into collections of related operations that can be represented in single panels. We use a regular expression grammar in order to partition our history. And each production of our regular expression grammar has a granularity level. And the granularity level specifies at what point the rule can fire. This allows us to create a hierarchical set of rule definitions that you saw in the videotape when we selected a panel and chose a different granularity. And the set of operations were parsed according to the new granularity, and the panel expanded. And we also performed the reverse operation, the coalescing, using these granularity levels. All of the productions in our grammar refer to command classes, object-based command classes, in an object-based command class hierarchy. This allows us to define rules that act upon whole families of operations at once. In the third step, we design the panels. We decide which objects are going to be included in these panels. The first step is to find all of the objects that participate in the operations and include those. The second step is to find an object in the scene, a nearby object, to use as a landmark to show where the operation is performed on the screen. In the third step, we tag the objects according to their role in the explanation. We'll tag the landmark object the landmark, and we'll tag the various arguments to the operation, the participating objects, according to what their role was in the operation. Finally, we'll choose a view. We'll choose a bounding box that includes all of the participatory objects in the landmark. In the fourth step, we render the objects in our panels according to how they've been tagged. So we can employ a different rendering technique depending upon the role of the object in the explanation. And currently, we render contextual objects in a grayed out fashion, as you saw in the videotape, and other objects in their normal fashion. We've used our history mechanism as a representation for a macro by example facility. First, I'll show you a videotape of our macro by example facility in action in Chimera, and then I'll tell you a little bit more about it.
Now I'm going to write a macro to left align two rectangles by demonstration. Initially, I draw two sample rectangles. Then I select 0 and 90 degree slope lines from the control panel. These are snap-dragging alignment lines. I next select two vertices to generate these alignment lines, the upper left vertex of the lower box and the lower right vertex of the upper box. I now select the top box, since this is the box that I'm going to move. I move the software cursor to the lower left vertex of this box. The software cursor and the selected box will gravitate towards intersections of alignment lines. Now I snap this top box to the appropriate intersection. The top box is now left aligned with the bottom one. The operations that I performed were captured in the history window below. I'll now select those operations that I want to be encapsulated into the macro. Here, all operations but the two add box operations in the beginning are to be used, since I want existing boxes to be arguments to the macro. After selecting the panels, I choose the macroize operation. This opens a macro builder window. This window contains all the panels that I selected from the history. I'll move this window on top of the history window. The next step is to select the arguments to the macro. To do this, I make the panels editable by selecting the checkbox at the bottom of the window. I can now select objects in these panels. First, I'll select the rectangle that remains fixed. I can do this from any panel where it's visible. I type the name of the argument in the text input widget and execute the make argument command. A panel is prepended to the beginning of the history, showing the argument name and the selected rectangle. Next, I select from one of the panels the rectangle that was moved during the alignment process and make it an argument too. I'll give it the name moved, and I'll execute the make argument command. Another panel is also generated at the beginning of the macro. Argument declarations are all placed at the beginning of macros, just as they appear at the beginning of conventional procedures. If I played back the operations that I had executed verbatim, they wouldn't do the right thing. It's necessary to generalize the macro to work in other contexts. Chimera has an inference engine that chooses the most likely interpretation of each command according to built-in heuristics. Here I have Chimera choose a likely generalization for the macro. The user can view the default generalizations and override them if necessary. For example, let's view the generalizations of the last panel in the history by executing the generalized panel command. This command generates a set of checklists that shows various generalizations for the operations in the panel and allows us to override those chosen by the system. For example, the first step of this panel was to select the object to be dragged. In the first checklist, the system shows that two possible interpretations of this operation are to select the argument named moved and to select a constant object. It chose the first interpretation. There are a number of other generalizations that were made for this panel. In this case, all of these generalizations are correct. I'm now going to apply our macro to a new scene. To do this, I switch to a new buffer and create two additional rectangles. Now I choose the invoke macro command from the menu. A little macro invocation window appears. I'm going to move it so that it's clearly visible. This window is labeled no name since I haven't named the macro yet. It contains two entries, one for each of the arguments that we declared. The first row is labeled fixed for the stationary argument. It contains two buttons, one to set the argument and the other to display it. The second row is for the argument named moved, and it contains two similar buttons. This time, I'll left align the lower rectangle with the upper one. I select the top rectangle and set it to be the fixed argument. I select the bottom rectangle and set it to be the moved argument. Now I press the apply button. The macro is invoked on the new scene.
As I mentioned earlier, the histories in our system are always on. Even if the history window isn't open at a particular moment in time, the history is being recorded. At any point in time, the user can open up the history window and select a set of operations to be encapsulated into a macro. So there are basically three steps in macro creation. The first step is to open up the history window and select the operations to be included in the macro by example. The next step is to parameterize the macro to select and name the arguments. And the third step is to generalize the operations of the macro to work in other contexts. The system will choose a generalization according to a built-in set of heuristics, but the user can view this generalization and modify it if they desire. Finally, generalization is done post facto. Generalization is done as a second step after the operations have been performed. It's not done during demonstration mode. This allows us to avoid having special commands to start and stop the definition of the macro. Here's an example of some of the of the types of generalizations that the system is capable of performing. If an object had been selected by the user, the system has to be able to determine a number of different reasons why that object may have been selected. And these are the different reasons that the system is currently capable of arriving at. The object may have been chosen because it's the argument to the macro, or an argument rather to the macro. It may have been a constant object. It may be the component of another object, a particular component of another object, or even a parent container containing a particular object. An object may have been selected because of a particular temporal reference. For example, it may have been an object that was created at a particular point in time. An object may have been chosen because of a particular position relationship that it has with other objects in the scene. And also, an object may have been selected because of the composition of these other reasons. For example, it may have been the third vertex of the second argument, for example. So the history representation that we have is used in a number of different ways by our macro by example facility. It's used for operation selection, both for selecting the operations to include in the macro, but also for selecting the operation that the user wants to see the generalization of, or change the generalization of. It's very important to have a visual representation of the macro in order to support editing operations on the macro. For example, we can use our visual representation, our editable graphical history representation, in order to insert new operations into the macro, as well as delete existing operations. The graphical history representation is useful for argument selection. The histories can be made editable, and the user can select objects in the panels and make them arguments and name them. The macro by example facility often uses the history representation itself in order to make particular information, in order to point out particular information to the user. For example, it's used during the generalization process, and one generalization might be that the value used at a particular step was that of a measurement taken earlier in the macro. So the generalization provided to the user might reference earlier panels, earlier states. Also, it's necessary to occasionally provide error messages to the user if the macro cannot be executed correctly. If a macro is invoked on unsuitable arguments, for example, an error might occur in trying to perform one step of the macro. And it's important to tell the user where the error occurred so that they can figure out why their macro didn't work on the available arguments. So in summary, I've shown you a number of different techniques today. Graphical search and replace, constraint-based search and replace, constraints for multiple snapshots, editable graphical histories, and macro by example facility. And even though all of these techniques are independently useful, they also interrelate. And they have a very synergistic relationship. The macro by example facility uses the graphical history representation both to support editing tasks as well as to support parameterization. And actually, I showed you a slide which listed something about 10 different ways the graphical histories support the macros by example. Graphical search is used as an iteration mechanism for the macros by example. We could perform a macro for all objects in the scene of a particular shape, for example. Constraint-based search and replace is essentially an extension to graphical search and replace. It allows the system to search for geometric relationships as well as complete shape. Constraint-based search and replace is essentially a technique to infer constraints from a static scene according to user-defined graphical rules. Constraints from multiple snapshots allow us to infer constraints from a dynamic scene, essentially steps in an animation. So there are a number of links between these components, links that indicate how they relate to one another conceptually, as well as how they work together in the Chimera system. There are also a number of potential links between the components that we haven't exploited yet, but that we could potentially add. For example, I mentioned to you that in our editable graphical history representation, we try to include a landmark object in each panel to show where in the scene the operation was performed. Well, right now we have a very ad hoc technique for choosing a reasonable landmark. It would be a good idea to make sure that the landmark was unique in the scene in order to better disambiguate where the operation was performed. So in order to make sure that the landmark object is unique, we could potentially use graphical search. So there's a link between editable graphical histories and graphical search. In fact, there are a number of additional links, and to extend the system, there are basically two different approaches we could take. We could try to fill in many of the potential links, essentially move the links from the right-hand side to the left-hand side to make a more unified programming by demonstration system, or graphical editing by demonstration system. We could also take each of these techniques and try to apply them to 3D and other domains and see how well they work. Any questions? Excuse me?
Sorry, I lost my voice. Does your system allow nesting of macros?
Right now, it does not allow the nesting of macros. I would like to add a facility for allowing macros to call macros. Another possibility is to allow recursively defined macros that call themselves. And I don't envision that is ever going to be implemented in my system. That second component. But I would like, before I package the system, a way to have macros that can call macros.
How easy is it to add a new category of constraints to the system? I don't know what categories you already have, what kind of constraints you already look for.
The constraints that we have in our system were selected basically by going back and looking at a number of other constraint-based graphical editor systems and determine what they found useful. We looked at Sketchpad and Juno and some other systems, and we chose basically the constraints that they used because we weren't interested in trying to figure out what sort of constraints people use. We were more interested in figuring out interesting techniques to use the constraints that other people had selected. It's fairly easy to add new constraints to the system, such that they can be used by the constraint-based search and replace component. It's a little bit more difficult to extend the constraints for multiple snapshots so that they work with the other newly added constraints, but that could be done as well. So, in order to add basically at the low level new constraints to the system, that's more or less trivial operation. That could be done in a day, and that would give you the capability of using these constraints in constraint-based search and replace. Adding them so that they could be used in constraints for multiple snapshots would probably take a few extra days.
Okay.
Have you had much experience with people actually trying to use the system for drawing, for managing drawings?
We have experience with people using certain components of the system, not the entire system. We have a lot of experience with people using graphical search and replace, and this was done one summer that I was at Xerox, and the code was released into their environment, and people are still using it, and they're updating it whenever the operating system gets updated, so that it still runs. So people have found graphical search and replace useful. The various other components of the system I've presented to people more or less independently and asked them to try to use it. And I tried to get a better sense as to how complex they found various aspects of the system that way. The graphical history representation has changed a lot since the initial version, partially in response to user comments. The initial version used up about twice as much screen real estate. People didn't like that at all, and they were slightly more difficult to understand. So the various elements have been modified in response to user comments. However, the user base of the current system, Chimera, is very small, in part because we chose a fairly eclectic environment in which to run the software. So I don't have as much experience as I'd like to see how people cope with the macros, by example, and the constraint-based search and replace, particularly. I'd like to do further experiments with that.
Have you thought about adding flow of control to your macros, for instance, to figure out which way the oak leaf should be placed? I noticed all the oak leaves curved to the right, no matter which side of the branch they were on, rather than always curving away from the branch.
We have considered adding flow of control to the macros, and that component of the system will probably not be done, not be completed in the near future. I have ideas as to how that could be added, how we could use constraints in order to specify branches, only perform one set of operations if a initial set of constraints is satisfied, for example. So we could essentially have like a left-hand panel in a graphical search and replace governing a macro, basically, macro execution. And something like that would be useful, but there are other things that I want to do first.
Okay.
What sort of performance limitations are there with this system? If I went to a CAD environment, would I still be able to use these techniques? Or?
For the most part, yes. They do run very quickly. The constraint-based search and replace, for example, making all lines tangent to the circle at an endpoint basically took 1/10 of a second, with excluding graphics update.
Which only had a few objects.
Which only had a few objects. However, that particular task is order n squared with a very and it's possible to prune out a lot of possible matches by using the technique I talked about earlier, where we use constraints in order to rule out a large number of possible matches. So I have used it in much larger scenes than that, and it still is run reasonably. And I think that could be used in CAD if environments.
Is there any opportunity to cache results for frequently applied operators?
We could do more caching for graphical search and replace. Right now, we're converting the objects into polylines every time we perform the match. We could cache a polyline representation for all the objects, and that would speed things up fairly dramatically.
I sort of noticed that all your examples are based on more or less regular geometric objects. Have you tried this where your constraints are like texture or fractal dimension, basically a more realistic scene where you wouldn't be able to use regular geometric things, like circles and squares and stuff?
Right. Well, as soon as you get away from regular geometric shapes, matching becomes a lot more difficult.
Exactly.
If you start dealing with things like paint systems, for example, matching becomes incredibly difficult because it becomes a vision task.
Right.
And you have to have techniques for doing very good approximate matches. Right now, the techniques we use in order to perform, to add tolerance to shape matches that allow us to match on objects that are not exact matches, are very accurate for the computer. Human beings do not find our matching metric very intuitive.
Or say you use regular objects with had texture maps, on the objects.
So apply the constraints to other properties aside from geometry, basically.
More or less, yeah.
That's something that I thought about a bit, but it really didn't seem as interesting to me. I'm sure that it would be possible to come up with examples, though, where it would be useful to apply it to other domains, such as color and fractal dimension. Yeah.
Do you see this as a standalone application that would apply for a variety of graphic applications, or would it have to be language specific to each application, which is freehand, Adobe Illustrator?
Right. Well, it's very important that the application be able to get at the display list of the objects in the scene. Now, if you do have a representation that allows you to view the objects in the scene as real objects rather than as bitmaps. For example, Pict does that. You could just run the program on the Pict representation, which would allow you to use this technique along with just about any application that works on your PC or Mac. You just have to find the proper object-based representation rather than pixel-based representation. Okay. Thank you.
Thank you.